basic electricity and electronics, alternating current. Number 5, oscilloscopes, using Lissajous patterns. In Part 4, you became familiar with measuring both voltage and frequency of AC waveforms. With a dual-trace oscilloscope, it is possible to compare the frequency and phase of two sine waves through the use of Lissajous patterns. These patterns are named in honor of the French physicist Jules-Antoine Lissajous, who first obtained these figures geometrically and optically.
Lissajous patterns are formed by comparing the amplitude of two sine waves. One sine wave controls the vertical position of the Lissajous pattern, and the other sine wave controls the horizontal position. To view these patterns, first perform the turn-on procedure. Since two waveforms will be compared, it is necessary to use both channels of the oscilloscope. First, set the vertical mode channel selector switch to both. This puts the oscilloscope in the dual trace mode. Next, set the vertical mode switch to chop. This position is used when viewing two low-frequency waveforms that require a horizontal time base setting of 0.5 milliseconds per division or more. This is typically the case when viewing waveforms less than 1,000 Hertz. The ALT position is used for viewing two waveforms that require a horizontal time base setting of 0.2 milliseconds per division to 0.05 microseconds per division. The add position displays the sum of the two waveforms. Set the A seconds per division selector to the XY position. This allows the oscilloscope to display Lissajous patterns. Now, set the input coupling switch of both channel 1 and channel 2 to the ground position. This allows you to center the trace. Next, adjust the channel 1, channel 2, and horizontal position controls to center the displayed dot on the screen. Then, set the input coupling switch of both channel 1 and channel 2 to the AC position. This allows you to measure the frequency of an unknown sine wave using Lissajous patterns. When doing this, it is necessary to have a known frequency or a frequency standard.
In this example, a signal generator set at 60 Hertz will be the frequency standard. An audio generator will be used to simulate the unknown frequency. Set the audio generator for approximately 120 Hertz. Connect the known frequency from the signal generator to the channel 1 input. Connect the unknown frequency from the audio generator to the channel 2 input. Adjust the channel 1 and channel 2 volts per division selectors so that the Lissajous pattern fills most of the screen. Adjust the frequency of the known signal until the displayed pattern is stable. The pattern should look like this. The ratio of the frequencies can be found by counting the number of loops which are tangent to the horizontal and vertical axes. In this example, there are 2 loops tangent to the horizontal axis and 1 loop tangent to the vertical axis.
To find the unknown frequency, multiply the known frequency by the ratio of the number of horizontal loops divided by the number of vertical loops. In this example, this equals 60 Hertz, which is the known frequency. Multiply 60 Hertz by the ratio of 2 horizontal loops divided by 1 vertical loop. Therefore, the unknown frequency is 120 Hertz. In order to check the unknown frequency by looking at the waveform, set the vertical mode channel selector switch to the channel 2 position. Then, set the A seconds per division selector to 2 milliseconds per division. The period of this unknown waveform equals approximately 4.25 divisions times 2 milliseconds per division. Therefore, the frequency equals 1 divided by 8.5 milliseconds, or approximately 120 hertz. Sine waves of a lower frequency than the known frequency can also be measured. In this example, the known frequency is 60 hertz. There are 2 horizontal loops and 3 vertical loops. Therefore, the unknown frequency is equal to 60 hertz, which is the known frequency, times the ratio of 2 horizontal loops divided by 3 vertical loops. The answer is 40 hertz.
Let's try a few for practice. In this example, the known frequency is 60 hertz. What is the unknown frequency? The unknown frequency equals 60 hertz, which is the known frequency, times the ratio of 3 horizontal loops divided by 2 vertical loops, or 90 hertz. Now, the known frequency is 1000 hertz. What is the unknown frequency? The unknown frequency equals 1000 hertz, which is the known frequency, times the ratio of 2 horizontal loops divided by 1 vertical loop. The answer is 2000 hertz. Now the known frequency is 15,000 hertz. What is the unknown frequency? The unknown frequency equals 15,000 hertz, which is the known frequency, times the ratio of 1 horizontal loop divided by 4 vertical loops. 15,000 multiplied by 1/4 equals 3,750 hertz. Now, the known frequency equals 100 hertz. What is the unknown frequency? The unknown frequency equals 100 hertz, which is the known frequency, times the ratio of 1 horizontal loop divided by 1 vertical loop, or 100 hertz.
Lissajous patterns can also be used to compare the phase shift of 2 waveforms of the same frequency. 2 waveforms are said to be in phase if both waveforms reach their maximum and minimum values at the same time. 2 waveforms are said to be out of phase if one waveform reaches its maximum and minimum values sometime before or after the other waveform. Phase difference is measured in degrees. The terms lead and lag are used to describe the relative position in time between 2 waveforms. In this example, E1 leads E2 by 180 degrees, or E2 lags E1 by 180 degrees. Therefore, the phase shift between the 2 waveforms is 180 degrees. The resulting Lissajous pattern for 180 degrees phase shift is displayed as a straight line leaning to the left. Therefore, these 2 waveforms are in phase. This example shows no phase shift or 0 degrees phase shift. The resulting Lissajous pattern for 0 degrees phase shift is displayed as a straight line leaning to the right.
This example shows a phase shift of 45 degrees. The resulting Lissajous pattern is displayed as an ellipse leaning to the right. In this example, there is 90 degrees of phase shift. The resulting Lissajous pattern is displayed as a circle. This example shows 135 degrees of phase shift. The resulting Lissajous pattern is displayed as an ellipse leaning to the left. Lissajous patterns will only show phase shifts of up to 180 degrees. Remember, Lissajous patterns do not show the relative position of the 2 waveforms. In the next program, magnetism and electromagnetism will be studied, and the basic principles of inductive circuits will be introduced.